This tutorial is about section 1.1, patterns in inductive reasoning. There are two types of reasoning that we know of. One is called inductive, the other is called deductive. This one focuses on inductive reasoning, which we will soon know to be as reasoning based on patterns. And I'm going to show you a numeric pattern that we're going to start with, and we're going to try to figure out the pattern. So, in this example, I'm going to give you the following numbers. We're going to start with 3, then go to 6, then go to 12, 24, and we are going to determine the next two on our own, etc., etc. Now, when you look at the first couple numbers here, it could be a couple things. To get from 3 to 6, I could have either multiplied this by 2, or I could have added 3. In order for a pattern to be true, the same thing has to be occurring between any two numbers in this pattern. So if I look at the next two numbers and I decide to add 3 here, I know that 6 plus 3 is not equal to 12. So there's a problem there. I can't use that plus 3 any longer because it only works for one pair of numbers. So let's try this multiplication by 2. Is 6 times 2 12? Yes, it is. Now let's check this for the next one. How about 12 times 2? Does that give me 24? Yes, it does. So in order to find the next numbers, this pattern should stay continuous throughout every two numbers that I have. So 24 times 2 is going to give me 48, and 48 times 2 is going to give me 96. And this pattern will continue forever. And this is just one kind of inductive reasoning that we're going to see. We may see some as well with pictures, so let's give one of those a try. So how about if I have a triangle and this top part is shaded, and the next figure that I have is also a triangle, but this time this corner is shaded. What do you think the next triangle is going to be looking like? And if you can see this, this is moving in a clockwise position. This piece of this triangle has moved to this corner. So if I follow this pattern again, if it's continuing to move clockwise, this is going to move over to this angle here of this triangle. So my next shape should have this part of my triangle shaded. So that's a little bit about inductive reasoning. The next thing that we have to talk about is what a conjecture is. I'm going to go ahead and erase this. We're going to talk about a conjecture. And in mathematics, a conjecture is a very basic idea. It's a very fancy name for a conclusion. And it is a conclusion based on inductive reasoning. So, we're going to take a look at a really neat example here. We're going to sum some odd numbers. So I'm going to take the very first odd number that's positive, which is 1. And when I add nothing to it, very simply gives me just 1 again. So now let's add that to the next odd number that we know of, which is 3. So 1 plus 3 I know is 4. Now, there's not really a clear pattern to any of this yet, so let's do another. So 1 plus 3 plus the next odd number, which is 5. And this gives me 9. So I want you to look at 1, 4, 9. I want you to try to think, as we're going through this, of what the pattern might be, because there is one. Now let's do the next one and see if this helps. 1 plus 3 plus 5, and now we're going to add the next odd number, which is 7. And this gives me 16. So when I look at this, and you may not see it right away, which is right. When I look at the very first line here, how many numbers do I see? I see 1. I'm going to write that over here. Just 1. I want you to look at the next line of numbers that we have. How many odd numbers do you see here? I see 1, 2. I'm going to write 2 right here. Now I want you to look at the next line. 1, 2, 3 numbers. I'm going to write 3 here. And then the next one happens to be 1, 2, 3, 4 numbers. So here. How can I make this 1, 2, 3, and 4 look just like 1, 4, 9, and 16? Do you see the pattern? Watch what happens if I square the numbers in red. 1 squared is 1, 2 squared is 4, 3 squared is 9, and 4 squared is 16. So the pattern here, my conjecture that I see is that, that's supposed to be a U, sorry, the sum of odd numbers is equal to the amount of odd numbers I have squared. So how many, or what do you think the value would be if I wanted to know the sum of the first 30 odd numbers? How would I do this if I follow this conjecture? So what I was able to determine here is that the sum of the odd numbers that I'm looking for is equal to the amount of odd numbers I have squared. So in this case, in purple, this is the sum of the first 30 odd numbers. Well, that means if I follow my conjecture, it should be whatever 30 squared is, which is 900. So that is what conjectures are. Conclusions based on inductive reasoning. Let's look over one more concept here. I'm going to go ahead and erase this page. The next thing that I need to talk to you about is what a counterexample is. And counterexamples are really important in mathematics for proofs and for proving a point. So counterexamples are examples for which the conjecture, which is a conclusion, is incorrect. So basically what a counterexample is doing is you're trying to prove that the conjecture that somebody else stated isn't right all the time. At least one place that you know of, the conjecture fails. So let's take a conjecture to start with. We'll do this in blue. So let's say I tell you that the difference of two integers is less than either integer. And you're not going to get very far in this problem if you don't know what an integer is. So let's refresh our memories real quick. Integers are whole numbers, positive and negative, and they include the number 0. So in order to start this, let's just pick 2 random numbers and see what happens. So let's take the example 9 minus 5, which we know to be 4. So this is just a difference of 2 integers, and let's see if what this conjecture is telling us is true. So the difference of the 2 integers is less than either integer. So this number here has to be less than either of the 2 integers that I subtracted. So I do know that 4 is less than 9, and 4 is also less than 5. So far my conjecture works. So where would it fail? So here is where your intuitiveness comes into play. You have to think outside the box. These are both positive numbers. What happens if I throw in a negative number in here? So let's try 9 minus negative 5, which whenever I subtract a negative, I know that that is the same thing as adding. So I know that 9 plus 5 is equal to 14. Now once again, if this conjecture is true all the time, this should work. So this number 14 should be less than both of the numbers that I subtracted. So to do this, how does 9 compare to 14? Is 14 less than 9? No, it is not. What about the next number? Is 14 less than negative 5? No, it is not. So this would be my counterexample. Not just one statement, but the whole entire thing. This whole piece is my counterexample. I have to tell that whoever wrote this conjecture, I need to give them a specific example. The specific example being this piece right here. And then what happens? And then proving to that person that, you know what, you are not right because this is coming out to be false. So in order to prove a conjecture is false, you only need one counterexample. That's it. So we have covered inductive reasoning. We have also covered conjectures and counterexamples, and you'll be quizzed over this very shortly. If you have any questions, please come and see me.